All right, so today we're going to be doing some transformations of trigonometric functions. Here's today's plan. So we're going to be moving trigonometric functions left to right, up and down today, as well as stretching them like we did last class. So we're going to need to break them down to each of the parameters in transformation form. So y equals af b x minus c plus d. This is pretty much the exact same thing we saw earlier this year. Instead of c and d, we use some different letters. I'll talk about that in just a second. But we're going to do all this with reference to the function f of x being either sine or cosine, of course. Now, the other thing I'm just going to let you know before I start here, I'm really going to focus on trying to get the time on this video to be under 20 minutes. If I don't make it there, I'll tell you what, any of the leftover questions, I'll just show you the slide briefly, and I'll get you to try them when we get to it. But anyway, I'm not going to waste any more time. Here we go. So for transformations, earlier in this course, we looked at this general form right here. I want to remind you that A was your vertical stretch. By the way, I'm using green today. Today's a green kind of day. But anyway, so the other thing is B was related to your horizontal stretch, and that's a factor of 1 over B. So what you're actually multiplying your x's by is 1 over B. You're not multiplying your x values by B, you're multiplying by 1 over B. H was a horizontal shift to the right. So if you had x minus 2 in here, for instance, you're going right 2. If it said x plus 2, then that tells you that h would have been negative 2, so you're really doing x minus negative 2. And if h was negative 2, that means you're going to 2 to the left instead. And then k, of course, was your vertical shift up. And the other thing that we remember from earlier this year was your nested brackets here, separating your b value from the rest of this stuff in here. Those are absolutely essential because otherwise it becomes a little bit confusing what's going on. And if you don't have them there, you just have to factor the b out, and then you find what your new h value was. This is going to work pretty much the same for trigonometry. We saw last class that A affected your amplitude, so in other words, how tall the function was, and B affected the period of the function in such that the period was equal to 1 over B, your horizontal stretch, times by 2 pi if you were in radians. If you were in degrees, it'd be 360, same idea. Now, instead of using H and K like what we used to do, your textbook is calling them C and D now in trigonometry. To tell you the honest truth, I have no idea why. I have no idea why they decided to change them for trigonometry and not for earlier in the year. It would have made more sense to say this was C and D at the beginning of the year, but that's just what your book does, so I'm following it so you don't get too confused. So trigonometric translations, I want you to recall from last class that y equals sine x starts at y is 0 when x is 0 and is going up. So in other words, when you have the sine graph, we're starting at our midline, going up. That's how sine begins. Now cosine, however, starts at y is 1, which is your maximum on cosine, when x is 0, of course, and is going down, as it would be from a maximum. Maximum is not going to continue going up. If it was, it wouldn't be a maximum, right? Now, also recall that both sine and cosine have a midline that horizontally divides the graph into 2 alternating halves. So on both of these, the midline is your x-axis. So see both of these graphs for that. Now, these characteristics are going to be vital for translating these functions left, right, up, and down. The characteristics I'm referring to in particular are where sine starts and where cosine starts, as we started looking at yesterday. So vertical translations is what we're going to begin with first, because these are a little bit easier in most people's opinion. When you vertically translate a trigonometric function, in other words, when you move it up or down, its midline is moving with it. That's really what we're focusing in on when we do a vertical translation. Your midline is actually going to be equal to your vertical translation always, right? So if you're going up 5 units, your midline is now up at positive 5. If you're going down 7 units, your midline is now at negative 7, and so on. So I want us to compare the graphs of y equals sine x and y equals sine x plus 1. So sine x is this red one here, and sine x plus 1 is the blue one. I want us to note the midlines. Now on sine x, of course, our midline is our x-axis, where it's just equal to 0. Right? Because we didn't go up or down, we're just 0, right? Now, as for sine x plus 1, however, notice this is 2, this would be 1, this is 0, right? You can just label 1 right here. It would be y equals 1 is your midline, right? That line right there would separate your function exactly in half, right? That's your midline. So in the general form, y equals af b x minus c plus d, your midline / vertical translation is the d. Right? So in other words, it's on the outside of the entire mess of stuff here. So whatever you're just adding or subtracting on the outside, that's your vertical translation. All right, horizontal translations, these are a bit of a different mess altogether. So when you horizontally translate a trig function, the original starting point moves with it. So remember, your original starting point depends on whether you're using sine or cosine, but that's really something I like focusing in on. You need to be mindful of whether you're working in degrees or radians here as well. If it doesn't say, you should always assume you're working in radians. Radians are going to be a lot more common in this chapter than they were even in chapter 4. So we do need to assume that we're using radians unless it explicitly tells you you're working in degrees. So I want us to compare the graphs of y equals cos x, which is the red one, and y equals cos x minus pi over 4, which is the blue one. Really what we should notice here is our starting point. This is a cosine graph, and cosine graphs start at their maximum. But the blue one, notice we've moved it to the right by pi over 4, because it's minus pi over 4 in here. So C equals pi over 4 in this case, just to really drive it home, right? So we're moving pi over 4 here. Notice that your starting point also moved to the right by pi over 4. And if you don't believe me that that's pi over 4, well, look, this is pi. You can chop it into 4 pieces, 1, 2, 3, 4. So that is pi over 4. It moved to the right by pi over 4. Your starting point is what's really going to help you here. If this was a sine graph starts at the midline going up. Your midline going up would have also moved to the right by pi over 4 units, just like it did here. Like, look here, there's a midline going up, even though it's not our starting point, it's our midline going up, and the midline going up just moved to the right, right? That's all that's happening here. So again, in the general form, your horizontal translation is C, just like it was at the beginning of the year. All right, phase shift. So in trigonometry, horizontal translations are sometimes called a phase shift. That's just a different way of saying a horizontal translation. And this one I do actually know why, unlike why they used C and D instead, but this is because sine and cosine, they're actually the same graph. Like, this is sine and this is cosine, right? They're the same graph, it's just they were shifted left or right by either pi over 2 if you're in radians or 90 degrees if you're in degrees, right? You could think of if sine was the original graph, well, notice we have a midline going up. The midline going up was just moved over here to negative 90 degrees. So you just moved it to the left by 90 degrees. Or if you considered cosine the original graph, well, cosine being the original graph, we just moved our maximum point to the right by 90 degrees. So it's like cosine is sine shifted to the left, and sine is cosine, but just shifted to the right, right? So they're the same graph, they were just shifted left or right. So we call it a phase shift. It's shifting from one phase, sine, to the other, cosine, or vice versa. All right, so we're going to complete this table here. We'll run through this pretty quick. Here's a couple equations. We'll want to talk about the transformations to the original graph, the range, and the x-intercepts within this very specific domain, as well as the y-intercept. So first of all, when we have this equation, sine x minus 30 degrees. Well, since it's minusing 30 degrees, our transformation is we moved it right by 30 degrees. Now, our range has to do with our y values. Now, I want you to notice, if we're just moving it to the right by 30 degrees, we're not moving it up or down, we're not stretching it vertically, so our range isn't changing. Now, for sine or cosine, your range, without any other things happening to it, should just be from -1 to +1. That's the normal range of sine and cosine. This one's going to be a little bit trickier. X-intercepts within 0 to 360 degrees. Well, let's just think real quickly. I'll draw it down here because that might make a little bit more sense. Usually a sine graph starts here, comes up, goes down, and then goes here. And of course, where it comes back, that would be at your 360-degree point. But we're moving this to the right by 30 degrees. So let's think about all of our x-intercepts that are usually within this. This first x-intercept is at 0. That's moving to the right by 30 degrees, so we can immediately say we have an x-intercept at 30 degrees. This other x-intercept is right in between 0 and 360, so naturally it would be 180 degrees. That also is moving to the right by 30 degrees, so we can say that that's now 210 degrees. This 360 is moving to the right by 30 degrees, so now it's 390 degrees, but look, it's no longer within our domain, so we don't have to include it. So these are our only x-intercepts. As for our y-intercepts, this one's going to be a little sillier. You don't really have much choice here with a y-intercept because y is going to move at much more unpredictable way. You're actually going to instead have to find your y-intercept the old-fashioned way. Plug in where x equals 0. So I'll even say that x equals 0. Plug x is 0 into this equation here. So make sure you're in degree mode in your calculator as I'm doing right now. So I'm going to go sine of 0 minus 30 degrees, which actually gives me a decent point. Y equals negative 0.5, which I bet we probably could have just figured out because, again, sine of negative 30 degrees is a reference angle of 30 degrees, and sine 30 is a special triangle. That's negative 1/2. Okay? Either way, though, we got it. Next up, this one, sine x plus 2. Notice how this plus 2 is on the outside of our original function. Because it's on the outside, that tells us we're moving it up 2. Okay? So since we're moving it up 2, this is going to affect our range. Our range is usually negative 1 to 1 on a normal plane sine graph. But we're moving everything up 2. So that means our lower bound of our range is going to have to move up by 2 points. So negative 1 going up by 2 points is going to bring up to positive 1. And 1 going up by 2 points is going to bring it up to 3, right? We didn't have any vertical stretch here, so we don't have to do anything more. The amplitude here is still 1. It's going up from a midline of 2 up to 3 and then down to 1. So that would still be our range. Now x-intercepts, this one's going to be kind of interesting on this. X-intercepts are where y is equal to 0, right? Well, what do we notice about this range? The graph is only occurring between y is 1 and y is 3. Your x-intercepts are defined by the term x-intercept as being where y equals 0. Is y ever equal to 0 within this range? Of course not. So there are none. There are no x-intercepts here. Whew, that actually made our life a little easier here. So thank goodness for this range, right? Now for our y-intercept, on the other hand, we should still just do the same thing we did before and plug in x is 0 straight into this. So if I plug x is 0 into that, I get sine 0 and then plus 2. And that actually just gives me y equals 2, which I guess makes sense because, again, usually our y-intercept for a normal sine graph is at 0. Y is 0 when x is 0 on sine. And if you're just moving everything up 2, I guess y would just move up to 2, right? That works just fine. Next one, these ones are a little bit more complicated. Transformations to the original graph for this first one here. Notice it's x plus 60 degrees. Don't get confused by this. Remember, horizontal stuff is backwards to what you think it would be. Really, this is saying x minus negative 60 degrees. Or in other words, we can say it's moving left 60 degrees. And this minus 1 is pretty clear, though. That's moving it down 1. Now, your range, of course, is only affected by whatever you're doing to your vertical components. So since we're moving down 1, our normal range of negative 1 to positive 1 is actually going to become negative 2 to positive, or not positive, just 0, right? Because 1 down 1 is 0. Ooh, now here's where it gets interesting. Your x-intercepts within 0 to 360. Ooh, let's break this down. So what I'm going to do is I'm actually going to draw a normal sine graph right here. Just a normal sine graph. But then below it down here, I'm going to draw my newly changed one, right? And there's a good reason why. We're looking for our x-intercepts. Our x-intercepts are where y is equal to 0. Notice now in our range that y is 0 is now our maximum point. I'm not going to look at my old x-intercepts anymore. I'm just going to look at my maximum points within that certain range, right? So my old my old maximum point within degrees, of course, would have actually been, let's see, 360, 180. It would have actually been at 90 degrees, okay? So at 90 degrees, I would have otherwise had a maximum. And remember, the maximum is going to become my new x-intercept because it's the top of my range. So this maximum at 90 degrees is actually getting moved over by 60 degrees to the left and then down 1. So it's now over here, right? And this point right now here is moved over 60 degrees to the left from 90 degrees, so we're actually now at 30 degrees for our maximum. If I continue cycling this through, eventually it's actually going to hit again, because we need to get one through full cycle at least through here. So we're going to have to determine this other one probably in a second here too, but let's just hold on for a moment. I'll write down 30 degrees. Okay, so I guess the other thing we could do is we could figure out where our next maximum would have been from here on. Well, if from 0 to 90 brought us to a maximum, then I guess from 360 plus another 90 onto it, so I guess that would be 450. Our next maximum would be 450 over here. Well, if we're moving that over 60 degrees, then that brings us to 390 degrees, because 450 minus 60 is 390. Oh, and thank goodness, that is actually outside of our domain here. So really, our only x-intercept, I guess, within our proper 360 degree window here is at 30 degrees. An alternative to doing this, like I just showed you how to do it just by hand, an alternative to doing this is you could throw this in your graphing calculator and graph it. and see if you can find that information. If you're more comfortable doing that, by all means, graph it in your graphing calculator. That would probably be easier. Just remember though, when you're putting degrees in here, you got to make sure that your calculator is set in degree mode. Now, as for a y-intercept, again, this one's a lot easier. Just plug in where x is 0 in here. So I'm going to plug x is 0 into this and get a number. I can tell you right now it's going to have to be an exact, well, it could be an exact value. I'll tell you what, we'll do an exact value and we'll do without an exact value. Without an exact value, I'll literally just throw 0 into that equation, and we get an absolute abomination of a number here. We're getting y equals negative 0.13397. I'll even write it down, 13397, blah, blah, blah. There's a bunch of other numbers after that. That really is not great, right? What we can look at, though, is when I plug x as 0 in here, we have sine 60. Now, sine 60, I hope you remember from chapter 4. If you don't, I don't blame you, because it's probably been a while if you're watching this after Easter. But sine 60, of course, comes out of your special triangle. So we should know that sine 60 is root 3 over 2. And what we're doing is we're just taking sine 60 and minusing 1 from it. So if we're doing root 3 over 2 minus 1, well, in order to get this to work, we really should have this over 2 as well. So I should say that this is, and I'll just erase it real quick. What I'll really say is it's root 3 over 2 minus, instead of 1, we'll put that as 2 over 2. And then that becomes root 3 minus 2 over 2. That would be a better way of putting it. It's still going to be a negative number because root 3 is actually smaller than 2, but you still get the idea. That's kind of an exact value of a y-intercept. Anyway, last one here. I hate how it's y minus 45, so let's move that over. Y equals sine x minus 45 degrees plus 45. Once we have it like this, we can see we're moving it right 45 degrees and we're moving it up by 45 units. Since we're moving it up 45 units, that's going to affect our range. Our range is usually -1 to +1, so the lower bound of our range now is 44, and our upper bound of our range now is 46. X-intercepts within this, woo, remember, x-intercepts are where y is equal to 0. There is no way y is equal to 0 within this, not even close, so there are none on this one. And then as for our x-intercept, this one's what we always like. We just throw in x is 0 into this, right? Again, though, sine being -45, that's actually technically, like if we want to do this as an exact value, it technically is an exact value. I'll even just write it over here. Sine of -45, that has a reference angle of 45 degrees, so we know we're going to be dealing with root 2 over 2 because that's a 45, 45, 90 triangle. But as messed up as this sounds, use the cast rule to determine, since you're down in this quadrant, because -45 degrees is down here, really sine should be negative, so we'll say that's negative root 2 over 2, and we still have to add 45 to it in the first place. So here we go. Negative root 2 over 2 plus 45 is really like saying negative root 2 over 2 plus 90 over 2, because that's 45 just written over 2, right? So this gives us an exact answer of negative root 2 plus 90 over 2. Or in other words, totally nuts. Like that's absolutely insane. But you know what? It is what it is. If you wanted to throw that right in your graph or in your calculator and find a approximate value like we did up here, by all means go for it. It didn't say it had to be exact, but I'm a perfectionist. I want it to be exact. All right, so we've only got a couple minutes left, and then I'll hold true to my word here. Suppose a sine graph that has undergone a vertical stretch and a vertical translation now has a range of 4 to 10. Drawing a picture on this, when we're looking for a midline and amplitude, drawing a picture on this, even if it's just an extremely rough sketch, can go a long way. Our minimum is 4, our maximum is 10. It's a sine graph that's only undergone a vertical stretch and a vertical translation, so nothing horizontal, so we know it started a midline going up. It's going to look something like this. Okay, we know the maximum point is 10, we know the minimum point is 4. We're asked, what is the midline, right? Because the midline is your vertical translation, and also what is the amplitude. A little bit of creative thought here can help you, but there's actually technically a formula for this. Remember, midline is really your D value here. We can say that D is equal to the average of these 2 points, okay? The average being, of course, your max plus your min divided by 2. Or in other words, 10 plus 4 divided by 2, which is 14 over 2, that would be 7. Ask yourself always when you do these questions, does it make sense that 7 is the midline here? Well, it certainly seems like it would be to me, right? It actually does seem like a good midline. So yes, I would say 7 does make sense. Now, for amplitude, we also have a formula for this one. And again, if you use a little bit of intuition, you'll probably be able to figure it out, but I'm rushing through this. So A is actually equal to max minus min divided by 2. It's just the halfway point between the difference between the two. So in other words, 10 minus 4 divided by 2, that's 6 divided by 2, so it would be 3. And again, now that we know our midline up here, you probably could have just counted that. The amplitude, again, is the distance above the midline that your max or your min is. So, of course, that would be 3. Do a couple more quick things here before I call it a wrap. Write the equation of a sine function that has a vertical displacement of 2 units down, 30 degrees to the left, period of 120 degrees, and an amplitude of 1. Period is an important thing to remember. Period, of course, is just where you take your horizontal stretch, so 1 over b, and times it by your normal complete period. Well, the normal complete period in degrees is 360 degrees, and we know the period in this question is 120 degrees, so you could solve for this by dividing by 360 and then rearranging it for b. Bottom line is, I'm pretty sure from this that b would equal 3. So we know b is 3. We know our amplitude is 1, that's our A value. We know our horizontal phase shift is 30 degrees to the left, so we'll be adding 30 degrees inside the brackets. And we also have a vertical displacement of 2 units down, so D is -2. Throwing this all together and keeping in mind it's a sine function, we can say y equals A, you know what, I'll write the whole thing out. A, F, B, X minus C plus D. In this question, F is sine, A is 1, so I'm not even going to write it. So we'll just say sine, square bracket, B is 3. Don't forget your nested bracket. X minus C, well, it's phase shift of 30 degrees to the left, so it's plus 30 degrees. Close the brackets off. Plus your vertical displacement, it's 2 units down, so we're going -2. That would be your equation for this one. Next one, write the equation of a cosine function that's been reflected in the x-axis. Okay, so the x-axis is this guy right here. If it's reflected in that, it's a vertical reflection. Has had a phase shift of pi/4 to the right, period of 3, and an amplitude of 4. Start with a period, because that's always the hardest thing to work with. Remember, period equals 1 over b times by your normal full period. Normal full period is 2 pi. You could see, in this case, if we're solving for b, you know, it might actually be easier in this one is if I said it was 3 equals 2 pi over b, and then times by b on both sides and divided by 3. Either way, b is going to equal 2 pi over 3. Yeah, that would work. B is 2 pi over 3. Good. We know our amplitude is 4. We're going pi/4 to the right, so that's going to be our C value, and it's vertically reflected, so A has to be negative. Let's throw all this together. Oh, and it's a cosine function, sorry. We'll throw it all together. Y equals A, which is -4 because it's a vertical reflection and amplitude is 4. Cosine is our function. Square bracket. B is 2 pi over 3. Bracket. X, we're going to the right, so it's -pi/4. End bracket. And do we have a vertical displacement? Certainly doesn't look like it. So in other words, that would be our final answer right there. Yes, we're almost done. I knew this was it. If you want to just do these on your own, you know what? I'll just change my rule that I started today with. If you want to do these on your own, pause here and pause here. Try them on your own. For everyone else, we're going to go through it. See the questions at the end. Skip to the end, I guess. So I'm going to go through these real quick. So 2 cos, all that, blah, 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 you can read it. Transformations to the original graph. Let's break this down. 2 is a vertical stretch by 2. The 1/4 is related to horizontal translation. We could say it's a horizontal stretch. So a horizontal stretch by 4 minus pi/12, and that means we're going pi/12 to the right. And then plus 3 on the end means we're going 3 up. Amplitude is going to be related not only, amplitude is only going to be related to your A value. Sorry, amplitude here is going to be 2. Your period is going to be related to your B value, so 1/4, but really you can just take the reciprocal of your B value, which is your horizontal stretch, so 4 times that by the normal period. Normal period for something with radians is 2 pi, so really we're dealing with 8 pi. And then the range, of course, this is where I was going to try to say it with amplitude here, but this is where things are going to get a little weirder. Your range is basically just your amplitude above your midline and your amplitude below your midline. Notice your midline here is 3, right? So if you were to draw this, the middle of the line here is 3, your amplitude is 2, so you're going 2 above your midline and 2 below your midline. Drawing it like this can maybe help. 2 above the midline is 5, 2 below the midline is 1, so our range here is from 1 until 5. Right? For this next one, let's look at this negative here. That's a vertical reflection. Okay. The 3 is related to our horizontal stretch. We have a horizontal stretch by 1/3. Pi is being added to this, so we're going left by 1 pi, and then -4 means we're going down 4. Amplitude here is just your A value. Notice A is -1. We don't like having a negative amplitude, so I'll say the amplitude is 1 here. Period is related to the horizontal stretch directly, so 1/3 times 2 pi. So 2 pi over 3 would be your period on this one, because you're just taking 2 pi and timesing it by 1/3. And then your range, of course, like I said before, it's related to your amplitude and to your midline. Our midline here is -4. Our amplitude is 1. We're going 1 above it and 1 below it. So 1 above -4 is -3, 1 below is -5, so that means our lower bound of our range is -5, and our upper bound of our range is -3. See, it's not so bad once you break it down like that. Last little part of the questions here. So 1/2 is on the outside there. That's your vertical stretch. So vertical stretch by 1/2. Careful on the inside here, though. There's no nested brackets. Let's just change that real quick. It's cosine 2. I'll do a square bracket here. 2x. Now you got to ask yourself, okay, if you're going to bounce 2 here, how do you get a -90? Easiest way to do that is just divide this -90 by 2. That gives us -45 degrees. And then, of course, the +1 on the outside. Once you have the nested brackets, now you're in the clear to start talking about your other horizontal stuff here. So we have a horizontal stretch, not by 2, but by 1/2. Then we're moving to the right by 45 degrees. And then we're moving up 1. Amplitude here is going to be your A value, so your amplitude is 1/2. Your period, of course, is just going to be your horizontal stretch times by the same unit as your equation. So 360 is usually what our period would be here, but we're timesing it by 1/2. So the period here is just 180 degrees. And then your range, use that strategy I showed you before. Your midline is at 1. You're going, what's our amplitude? Oh, 1/2. You're going 1/2 above it and 1/2 below it. So we're going from 1.5 to 0.5. So our range here is 0.5 to 1.5. Remember, it's minimum to maximum, always. Last one here, again, similar problem from before. We don't have our nested brackets. 4x minus, divide that by 4, so minus pi over 4. Make those square brackets on the outside. I don't know why I keep forgetting that. We don't have a vertical stretch here, so we'll ignore that. We do have a horizontal stretch, though. So a horizontal stretch by 1/4. We're moving right pi over 4, and we're moving up 5. Amplitude here is just going to be 1 because we didn't have an A value otherwise. The period, using the same units here are, of course, radians. So we'll take our horizontal stretch, 1/4, and times that by 2 pi. 2 pi times 1/4 is 2 pi over 4, or in other words, 1 pi over 2. That would be the period. And then the range, use that strategy one more time, 5 going up by the amplitude. So up 1 is 6, down 1 is 4. So our range here is from 4 to 6. We're done. So for practice, page 250, questions 1 to 7, 11, and 13. Those would be really good questions to work on. For those of you who stuck through the whole thing, thank you. For those of you who just skipped the end here, no worries. Again, don't feel like you missed too much. You can always just check the answers in there. I don't feel like wasting a lot of your time. I'm trying to keep these videos as short as possible, but it's hard to fit all this much information in around 20 minutes, as I hope you guys understand. Anyway, remember, if you ever need me, contact me by email or by remind, and best of luck.